So the first talk is Valery Rubakov. Bounds, Genesis, how did the universe start? Please.
Раз, два. Слышно? Английский, да?
Да, потому что там. Okay, so let me first of all congratulate all our all these 7 people. 4 of them are here. Smirnov, Vladimir, and Anatoly Radyushkin are with us with Zoom, and I'm sure Vladimir Belakov is joining. So that's very interesting, a special event, of course, and I'm very happy to participate in this event. And of course, everybody, I'm sure, will enjoy this. So even though most of the works by these 7 people are not dedicated to cosmology, I'm going to discuss cosmology here. And that's the title, Bounds, Genesis, and it all has to do with very, very early stages of cosmological evolution. Here are my collaborators on this business, and of course, there are several groups that are interested in similar issues. So as an introduction, I'm going to discuss homogeneous isotropic spatially flat universe. And unlike many other models, including inflation, what I'm interested in is an alternative which assumes that the universe was never singular. There was no real singularity in the past, or even classical singularity. So the universe was classical and evolved classically during its entire history. And there are 2 options. One is that the universe started as very big and empty, very slowly evolving, but it was contracting instead of expanding as it is today, meaning that the Hubble parameter in particular was negative early in the history of the universe. The scale factor was very large in the early history of the universe. So the universe was like ours, but time reversed. Of course, then it should contract faster and faster, and at some point there must be some, miracle happening, and this contracting epoch, of course, should become expanding, and in the end, the conventional hot epoch or inflation should begin. That's one of the scenarios which is known as bouncing universe scenario. Another, which is more recent, the bouncing universe is with us, with our predecessors for many, many years, and it's very hard even to say who was the proposed the idea. But Genesis is another scenario which is not that old. It's about 10 years old, and the scenario is that the universe starts from Minkowskian space-time, empty and not evolving. And by some miracle, the energy density increases. The expansion rate, therefore, also increases. So the universe expands faster and faster. And again, there must be some, transition epoch to conventional hot epoch. So the Hubble parameter in this case is 0 in the past, and then it grows, and then today it is decreasing. Motivation for these scenarios is numerous. One is that simply curiosity. We always know about inflation, but it's always good to have alternatives. The second thing is that there is no initial singularity, and some people think that it might be an interesting option. Now, unlike inflation, it's not obvious that the standard cosmological problems are solved, but in some sense they are. The horizon problem is solved because the evolution of the universe is infinite in time. Curvature problem can be solved by specific way the universe contracts in the contracting universe, or by the initial assumption about the initial state. And one more thing is that this set of scenarios is interesting from the viewpoint that there was a very long period, infinitely long in fact, period of very slow contraction or expansion. And the assumption is that there was no matter at that time. The matter energy density was absent, zero. And if there were cosmological constant, and that there is some relaxation mechanism for the cosmological constant, then this relaxation mechanism could work at this prehistoric epoch. That's useful if you think about cosmological constant and think about the way you can relax the cosmological constant. The prerequisite is that you have to have very long prehistory in the evolution of the universe, and these scenarios do the job. The problems with all these scenarios is that it's not that easy to generate the necessary initial homogeneities in the universe that in the end become form the galaxies, cluster of galaxies, all the structure in the universe. We need to create a very special kind of initial perturbations, and that's not very easy. Now, nevertheless, if you think about the this prehistoric epoch, then you see the Hubble parameter increases. In all these cases, there is an epoch when the Hubble parameter increases in time, and that's within general relativity is only possible if you violate the null energy condition, what's called null energy condition, which in homogeneous and isotropic case means that the effective pressure, the spatial components of energy momentum tensor, is negative, and it's even more negative than minus energy density. Okay, and that's clear from, for example, one of the Einstein equations, which relates the time derivative of the Hubble parameter with this combination: pressure plus energy density. And to have this left-hand side positive, you need that the pressure is strongly negative, more negative than minus energy density. And in fact, if the opposite happens, if the null energy condition is not violated, then there is a Penrose theorem saying that there was a singularity in the past, always. So if you want to avoid singularity in the past, then you should violate the null energy condition, which is not very simple. It's fairly straightforward to check that if you have conventional field theory, for example, scalar field theory or vector field theory, conventional field theory, then you never violate the null energy condition. You always get into the problem with instabilities of two different sorts. One is what's called ghost instability, meaning that the energy density of energy of a particle is negative instead of being positive. The Lagrangian has wrong sign in it, so energy density is negative, and that's a catastrophic vacuum instability. You can create particles, ghosts, these particles with energy, negative energy out of vacuum together with conventional particles, and this means vacuum instability. Or in other cases, you have gradient instabilities, in which case the gradient term in the Lagrangian has wrong sign, and this means that instead of hyperbolic equation of motion, hyperbolic field equation, you have elliptic field equation, and the energy of excitation is imaginary. All excitations delta pi is the field, generic field. In this case, increase in time, and that's gradient instability, or sometimes called yes.
Saying about violation of null energy condition by classical energy momentum tensor?
Yes.
Only. Okay.
Yeah, I mean, yes. Okay, so what I'm going to concentrate in this talk is the way you can effectively violate the null energy condition, and for that you need unconventional field theories. If you want to be in the classical field theory or weakly interacting quantum field theory, then you would like to have violation of null energy condition. For that, you need theories with unconventional properties. And the simplest case is what's called Hornbesky theories. The idea is that, in fact, you can have scalar tensor theories of gravity, which has second derivatives in the Lagrangian. Normally, you tend to avoid second derivatives in the Lagrangian because then you typically have higher order equations of motion, fourth order in derivatives, for example, and then you have what's called Ostrogradsky instability. Extra degrees of freedom, which are ghostly, which have properties of ghosts. However, that's not necessary. Namely, there are particular classes of theories which are called Hornbesky theories today, and they were reinvented many times under different names. The idea is that you may have field theory which has second derivative terms in the Lagrangian, and nevertheless, your field equations are second order. You don't have higher order field equations. The simplest case is shown here. Pi is my scalar field. I will denote the scalar field in this game by pi. Pi is a scalar field. X is its gradient term, gradient squared, four-dimensional gradient squared. And this is conventional, more or less conventional. F is more or less conventional term in the Lagrangian with first derivatives only. However, there is you can add the extra term like here, which explicitly contains the second derivative of your scalar field, and that appears to be a dangerous theory. However, you can check that the field equations are second order. There is no pathologies, and furthermore, you can construct explicit examples of stable null energy condition violation. And this way, you can describe early stages of genesis or period around the bounds in the bouncing universe. However, this is not so simple. These things are not so simple, and it's known under the name of no-go theorem in these Hornbesky theories. Namely, if you would like to have complete cosmologies that start from minus infinity in time and end up at very large positive times, then first of all, people have found by trying to construct explicit examples that you always have a problem. Either you have a big rip singularity in future, the extremely infinitely fast expansion of the universe in the future, or you have one of the instabilities I was alluding to, the gradient of ghost instability, and there are numerous explicit examples that have shown that this is always the case. And it turns out that you cannot avoid such an instability, and that's no-go theory. Let me briefly explain what is this no-go theorem based on. First of all, this is the most general Hornbesky theory, which has second-order Einstein equations and second-order scalar field equations. There are two terms which I have already written. These are on the first line here. And there are two more terms which involve an arbitrary function again of the field and its derivative. R is the scalar curvature, G mu is the Einstein tensor. So this is very, well-defined theory. It has four functions, free functions in it, but otherwise it has very definite structure of the second derivative terms. So you are dealing with modified gravity, scalar tensor theory of gravity, and then the no-go theorem goes like this. You study evolution of perturbations about homogeneous and isotropic universe, and these perturbations can be characterized by traceless transverse part, which are essentially gravitational waves, Hij, and the scalar part, zeta, which is the what's called scalar perturbation. So you have 3 degrees of freedom, two degrees of freedom associated with gravitational waves, 2 polarizations, and another degree of freedom associated with the scalar. Now, the quadratic Lagrangian for perturbations these perturbations about homogeneous and isotropic universe involve, of course, the conventional terms, and these are only first order terms in the Lagrangian perturbations. And there are coefficients here which depend on the Lagrangian itself and solution you're talking about. And what you need for the absence of instabilities is that all these terms, all these coefficients must be positive. Otherwise, here, this coefficient determines, for example, G determines for you the whether you have a ghost or real or conventional field. Positive G means you have conventional field. Negative G means that you have a ghost, etc. And negative F means that you have a gradient instability. So you need the Lagrangian terms all have conventional signs. Now, the important thing is that, of course, you should evaluate these expressions here, and they are pretty complicated, as you might imagine. I just have written expressions for terms entering these functions here, these coefficients here, and I just wanted to scare you with all these, technical details. But the main point is that the sum of the two coefficients, both of which must be positive, in this Hromdevsky theory turns out, for some unknown reason, to be a total time derivative of a certain combination, which is never zero, because in the numerator here, you always have positive quantity, and the denominator cannot be infinite, otherwise you have a singularity. So once this psi is never zero, and the right-hand side here is positive, then you can easily convince yourself that this equation cannot be true, provided that you are dealing with conventional bouncing or genesis scenarios, because if both of these integrals of the right-hand side diverge both at minus infinity in time and at plus infinity in time, then this integrated form of this equation here tells you that this psi must always cross zero, which cannot be the case in the non-singular universe. So once you have bounds, conventional bounds, or genesis where the scale factor is never zero, is always bounded from below, it's always positive and bounded from below, these integrals are divergent, and that's it. This is a no-go thing. You can't have bouncing universe or genesis in Hromdevsky theory. Now, and this explains how this happens, how you convince yourself that the divergence of this integral means that your psi should always cross zero. And in fact, this argument works even if you add more fields, more conventional matter obeying the net null energy condition, or more Hromdevsky terms, Hromdevsky fields. In all cases, you have this no-go theorem. Now, of course, once you have a theorem, you want to figure out how you can avoid this theorem. And the one way to avoid the theorem is this one. I think it's pretty interesting. You might think of this integral, which is crucial for the argument here. You may think that this integral at minus infinity in time is actually convergent. Okay? And that's interesting. If you think of bouncing universe or genesis, this A is always positive and bounded from below. So for convergence of this integral, you need these terms to tend to zero at minus infinity in time. Now let me recall that these are coefficients of the kinetic terms in the Lagrangians, and effectively these are Planck masses squared. Okay, so these F and G are actually analogs of Planck masses. So when I say that these terms, that these F's and G's go to zero at minus infinity time, this means that you're dealing with strong gravity. The Planck masses tend to zero at minus infinity in time. In this way, you can avoid evade the no-go theorem, because gravity is tricky. Effective Planck masses vanish at minus infinity. The gravity is strong, so you may face strong coupling problem. Okay, and the question is, can you trust the classical field theory for describing your background evolution in the first place? Right? You have low energy scale of gravitational physics. The Planck scale is effectively very low. Now the question is, can you really use classical field theory to describe the evolution of the universe? And the answer is yes, sometimes. Namely, what you have to do, you have to compare the classical scale of evolution, which is the Hubble parameter or its derivative, and this is essentially minus t at minus infinity inverse. So it's low. You have to compare it with the strong coupling scale inherent in your quantum field. Okay, and as an example, if you look at the gravitational waves, tensor perturbations, then this is the quadratic part. But of course, there are interaction terms, and this is the cubic interaction term in the for the tensor perturbations. Okay, importantly, what it has there is the same coefficient in here as here. Okay, so if you then estimate the strong coupling, quantum strong coupling scale, then this strong coupling scale has is just the square root of this f. Okay, if you canonically normalize, then you immediately see that this is the energy scale of your quantum theory. Okay, so your f goes to zero, so your strong coupling scale goes to zero, energy scale. But if it goes to zero slower than the classical scale 1 over t, like this, then you are in good shape. Your classical evolution of the universe is legitimate, but the theory is very strange. Namely, you have low Planck scale, much lower than all the energy scales of your say standard model, for example. So you are dealing with real quantum gravity at the minus infinity in time, and all interactions, all masses are higher than the Planck scale at that time, and the gravity is the strongest force. That's very counterintuitive, but it appears that it doesn't contradict anything. That's one option. And in this case, in this way, you can construct complete cosmologies by simply, choosing your free functions. You have several free functions of your scalar field is derivative in here. Then you can play with these free functions to design essentially the cosmological model which is desirable, whatever you like. For example, you choose your favorite Hubble parameter, like here, to describe bounds. You can use freedom in the field redefinitions to take your classical field linear in time, and then you design your functions in such a way that you have all the requirements satisfied at infinity plus infinity in time. You field is conventional scalar field here, so that you are dealing with very usual conventional epoch with massive scalar field driving the expansion of the universe. And in the past, you have strong gravity. So the field equations are satisfied, stability conditions are satisfied, then that's what you have to cook up. And also you want to avoid strong coupling problem. And that can be done. This is a simple example. Here's the behavior of the Hubble parameter. It's negative, it's bounds. The Hubble parameter is negative. Then there is a bounce when the Hubble parameter crosses zero, and then it decreases as it does today. So all the perturbations are healthy. The sound speed is less than 1. So there are no superluminal propagation of perturbations here. So the model is healthy. Right. So let me describe yet another approach, and another approach has to do with even more complicated theories than Hordetsky. Namely, it turns out, again, very unusual situation, that Hordetsky is not the most general healthy skeleton of theory without ghosts, with one scale degree of freedom. The point is that you may have a theory with second derivatives in the Lagrangian. The variation of action leads the high derivative equations of motion, so that offhand you have an instability there. However, they can be combined in such a way that the resulting set of field equations is actually secondary. That's known under the name of the general higher order scale tensor theory, and it's relatively recent development. One subclass is simple, and it can be understood why you don't have any pathology. The point is that you may think of making field redefinition. The first term in this field redefinition is simply the conformal transformation of metric. However, you may have extra term which contains derivative of the field. Okay, and that's what is called this formal transformation. The name is due to Bekenstein, same Bekenstein as Hawking-Bekenstein. And then, if you start off with Hordetsky theory, you make the disformal transformation, then you end up with one of the versions of these post theories, which is known as beyond Hordetsky. It contains, besides the term that I described before, it contains an extra term of this form. Okay? And then the point here is that it's a formal trick. This transformation may be singular, and if it is singular, then the theories, the initial Hordetsky theory and the Tost theory are no longer equivalent because of the singularity of the field definitions involved. In that case, you again have the same property that the terms in the scalar Lagrangian, in the Lagrangian perturbations, which must be positive, are again proportional to the derivative of a certain combination of your Lagrangian functions. But this combination here contains an extra term, which is proportional to this particular F4, the new term, which is beyond Hordetsky. And since there is this extra term, then there is no guarantee that this psi never crosses zero. It can cross zero. You can design a model in such a way that this psi crosses zero. The right-hand side is always positive. Scale factor is always greater than something, and still you can have healthy theory. Again, you can construct and create models by choosing particular form of your Lagrangian function. The problem, nevertheless, remains, which is not yet understood completely. Namely, in all these host theories, once you add extra scalars, extra terms, extra meta, then you face superluminarity problem. Some of the perturbations necessarily become superluminal. One of the models is written here. One of the models is always superluminal. And superluminarity is not a nice property. It shows that this theory, such a theory with superluminal propagation, about some backgrounds, this theory cannot descend from Lorentz invariant ultraviolet complete theory. So there is a problem. So let me conclude. To conclude, first of all, constructing complete, let me emphasize, complete meaning that time can become very large negative and very large positive. Constructing complete non-singular cosmologies is actually difficult. First of all, it requires, when in scalar tensor gravities, it requires non-trivial kinetic terms, gradient terms. The bounce epoch itself and aerogenesis epoch itself are not so problematic. You can easily construct bounce, period of bounce and aerogenesis without any pathologies. However, almost all complete cosmologies are plagued with instability, which is a no-go theorem I alluded to. There is one way out, which has to do with strong gravity, in the past, the gravity in the past is the strongest force. So that's pretty unusual situation where all the Planck scale, Planck energy scale, oops. The Planck energy scale is very low, lower than any other energy scale in our field. Nevertheless, it's a healthy theory, and the strong coupling problem does not forbid you to consider the classical evolution. Another way out is to go beyond Hordesky and host theories, and then there is a remaining problem with superluminarity, and if you want to avoid superluminarity, you have to impose extra non-linear constraints on the function of the Lagrangian. This may be too high a price to pay, but that's still an interesting option. So let me conclude by saying that the theories with host or Hordesky theories beyond Hordesky might be interesting from other viewpoints, namely, without any reference to cosmology any longer. First of all, the same null energy condition forbids you to have Lorentzian wormholes. The geometry is like this, the solutions to the field equations, interstellar, basically. That's forbidden by the analogy condition, and if the analogy condition is violated, then you might have static wormholes, you may have interstellar in your theory. It's still an unsolved question, unsolved problem, because studying the stability of you can easily construct solutions of this sort, but studying stability of the solutions is really very, very difficult, and it hasn't been done. The complete study hasn't been done. Another is whether you can create a universe in the laboratory. That's another side question. Namely, you might ask, if you collect a lot of matter in a small regional space, can you start a new universe? Can you create a universe in the laboratory? And again, if you have the null energy condition, then it is forbidden. This issue was raised actually quite some time ago. It was understood already at that time that it's not possible. Again, because of the null energy condition, you have to have a singularity in the past by Penrose theorem. But once you violate the null energy condition, then again, you might think of creating a universe in the laboratory, theoretically, for the time being. So there are many questions. There are many questions that have been raised again after many years of stagnation. There are many questions that have been raised again, and there are many questions which have not been answered yet. And we have a lot more to understand in the future.
Thank you very much. So, thank you. We can have few questions. Yes. Wait a second. For those who are in Zoom.
The last epoch, starting from some time, the prediction of standard cosmology and your theory differ, yes? And what's the time? So the predictions say the energies, say 1 TeV, are the same.
Well, TeV is not, I mean, probably it's not clear what is the scale. The issue is at what energy scale does the transition to conventional epoch occur? Okay, and then it can be any. It might start from Planck down to say TeV or 100 GeV. It's not clear. But
do you have some bound? Say, I think 1 electron volt is
no, 1 electron volt is
the same, I believe.
It is definitely ruled out. We know that the universe was had temperature at least a couple of MeV. mega electron volt. That we know for sure. That's the epoch of nuclear synthesis, neutrino decoupling. We are pretty sure that there was such an epoch. So all the temperatures must be higher. But maybe GeV.
So GeV is not excluded.
It's not ruled out.
Very strange.
Maybe will be soon.
Yeah, it depends on if we understand what the dark matter is, how it was created, what is the
No,
well,
at least this is something which might be close
yeah, this may be,
to touch.
yeah, that might be figured out at some point.
Yes. There.
May I ask a question? How is the organization? Okay. May I ask a question?
Ira, please.
Okay. Please. Okay. First of all, the bound solution for cosmology. What is your expectation for typical scale? Is it a Planck or this is a cosmic scales?
Well, I can't rule out any of the options. It could be Planck scale, or it could be, as we discussed, it could be GeV scale. And I'm open-minded in this sense. I think it should be quite a bit higher than say TeV, because otherwise it would be difficult to create dark matter in the universe. It would be difficult to explain baryon symmetry, but even that is not necessarily the case. So I'm open-minded.
Thank you, Sasha.
Thank you.
Hello, Valery. I have one question concerning limit of Planck mass goes to 0, because it's pure quantum world in this case, and but this consideration is pure classical. How to make it coherent?
Yeah, that's exactly the issue we were concerned with. Namely, you have a classical evolution, right? The problem is you have a classical, you think of classical description of the cosmological evolution, right? And you also have very low energy scale of quantum gravity. Now, which scale is lower? Classical evolution is slow. So its intrinsic energy scale of classical evolution is also very low. It goes like 1/t, where t is time. Time goes to minus infinity. So the issue is which scale is higher. And it turns out that you can easily arrange things in such a way that the quantum scale is still much higher than the classical scale. And then you are in good shape. You can't describe, quantum electrodynamics any longer because your electron is heavier than the Planck mass, than the effective Planck mass, but you can describe the evolution of the universe in classical terms.
Right. Well, since I don't see any more questions, let's thank the speaker again.
Thank you.
And we come to the next talk. Which is Eduard Boos model with induced spontaneously broken symmetry chain. Please.
Его надо на полный экран. Could I start?
Yes, you can start.
So, first of all, dear colleagues, it's a great pleasure for me to be here in such a remarkable event. And let me start by congratulating all our friends and colleagues for such a great event what they have organized for us. In fact, on behalf of scientists of our institute, which is Kabeltsyn Institute of Moscow State University, we have prepared some greeting cards for all of you, and maybe then we discuss with organizers how to send these cards, how to distribute to those our friends who are not in the auditorium today. In fact, so how should I move? Well, before I start the discussion of my talk, I would like to remind myself and tell you that some time ago, you know, a friend of mine, Mikhail Shaposhnikov, with whom we are collaborating for many years in CMS, because of some completely different, he told me one clever phrase that, Eduard, look, if something is not needed to anyone or to anything, then it's probably wrong or completely useless or something. So probably things what I am going to discuss is of that sort, but nevertheless, I don't know. Okay, let me start from sort of motivation and introduction. And that is the question which we all somehow try to address, and that is what we are wondering about. What is a new scale after standard model? And I remind you that before the start of the Large Hadron Collider, we have a very good theorem, so-called no-lose theorem, which was proved by analyzing the unitary behavior of the amplitudes of scattering of longitudinal massive gauge bosons in the standard model. And the answer of that analysis was that there might be in principle two situations, either somewhat rather light Higgs should exist, or at the scale about 1 TeV, some new physics should show up. But we know now the Higgs boson was found, and those arguments are disputed. And at the moment, we don't have such a theorem like we had before the LHC start. And we don't know, in fact, are there some other scales which would be acceptable for the LHC or even for FCC images. Well, also, I would remind you that the standard model itself is a perfect renormalizable theory, which works very well up to very high scales. But of course, if there are some new physics and some new particles which interact with our Higgs boson, it may, through the loop, give a contribution to the Higgs mass parameter. And that contribution would be proportional to that mass, which are, you know, this rotating in the loop, times a log of new scale. And it would be very natural to assume that the mass of this object, of this new object, is of the order of the new scale. And we will have some strong quadratic behavior with respect to the new scale, contributing to that correction to the Higgs mass. However, it happens so only in case if the coupling of our new particle is rather large, but we don't know, and that coupling could be in fact very small. And even those arguments, which are so-called little hierarchy problem, do not give us some solid arguments for new physics, as we in fact thought some time ago. Moreover, you see that experimental limits from both collaborations, CMS and ATLAS, somehow moved further and further in energy scales. And now, for many extensions of the standard model, we already excluded some regions up to few TVs, or sometimes even up to 10 TeV, which somehow, you know, makes all of us a little bit nervous what's going on. Many theories which we expected to be probably the very good and correct extension of the standard model are either already ruled out completely, or somehow the available parameters may somehow shrink quite significantly. In fact, I would also, I should stress that those kind of negative results are extremely important for moving further in understanding what is going on. But well, in fact, what we know precisely about scales, that we have Planck scale, which is about 10 to 19 GeV, and we have our electroweak scale, which is about 10 to 2 GeV or something. We know that from different kind of physics, some other scales appeared. For instance, a grand unification scale, which is 10 to 15 and 10 to 16 GeV, or neutrino seesaw mechanism give us something like 10 to 12 to 10 to 13 GeV. There's arguments with metastability of standard model vacuum, which are people here in the auditorium know very well, much better than I do. It's about 10 to 10 or 10 to 11 GeV. Some BSM models, which were listed in previous slides, some SUSY extensions, for instance, predict scales like TV or even 10 TV, but probably, being less and less natural. But nevertheless, such scenarios still exist, and many people are discussing them. But we do not know how many of these intermediate scales are, what the relations between them, how, if there are some intermediate scales, how transitions from one scale to another scale goes on. So we don't know any of these things. Well, another thing which I also like to remind you, this is is invisible here, well-known standard model Lagrangian for the Higgs field, and due to Broughton-Glare and Higgs mechanism of spontaneous symmetry breaking, we will end up with well-known Lagrangian for the Higgs field. You see, predicting all the vertices, which allowed us to compute all the production cross-section, all decay rates, and so on and so forth. And finally, all this knowledge led to the Higgs discovery. But some wonder or sort of question remained that the mu parameter here in the Lagrangian, very well familiar for all of you, is negative. And the question, why this parameter is negative? Okay, the answer is, it's negative, and who cares? Negative, why not? But there were many attempts to understand why it could be negative. And one answer, which was discussed in many papers before, was related to the idea of induced symmetry breaking. The idea is the following: suppose you have two Lagrangians, so two levels of Lagrangians, 1 and 2, with some mixing between those complex scalar field, and some, their gauge with respect to some gauge group, doesn't matter which group here is. And suppose that we have such a situation when mu1 squared parameter is precisely equal to 0, while mu squared 2 is negative and not 0. And then on that level 2, the spontaneous symmetry breaking takes place, which immediately lead to appearing of effective mu squared parameters for the level H1, which would lead further to spontaneous symmetry breaking on the level 1. Well, for such a simple situation, of course, you may write all relations explicitly. Here is the quadratic form for the scalar field, which has appeared here with a mass matrix, which is presenting here, and you can diagonalize this matrix in order to find masses of the scalar state with definite masses, and that is the exact formulas which are present here. V2 is the vacuum expectation value of the second level, and V1 is just simply proportional to V2 with, and that is the mixing coefficient, which is assumed to be positive. In case, if you assume that those mixings are small, then you immediately can solve this and to find that the relation between V2 squared and M2 squared is very familiar from the standard model. It's looks like very similar. And M1, which is proportional to V2 and to mixing coefficient. And of course, in that case, M1 is much smaller than M2. Well, that idea can be generalized to another model, and that is what I wanted to show you. And this model looks like, you see, suppose you have a theory which some n levels of that kind, as I described before. At each level, you have scalar field, some gauging with respect to some gauge field, plus some Lagrangian of possible other fields, fermions or whatever, on that level, and so on and so forth. And the assumption is that the mixing coefficient occurs between neighbors in that chain of coupled Lagrangians. And you see, what happened if we assume that all the parameters mu squared are equal to 0 except one, the latest one. Then also, if we assume that all mixings are rather small, as given here, then one immediately can understand what will go on. You see, that is our profile of the vacuum in each level. And once the spontaneous symmetry breaking occur at the highest level, let's call it Planck, whatever Planck is. And the lowest level, let's call it electroweak of course, in common marks. You see, once phase transition happens here, then it would somehow induce the appearing of mu squared term in the next level, and next spontaneous symmetry will take place, and so on and so forth, up to the very end. Having those parameters, which is, the position of vacuum expectation value, smaller and smaller. Well, if you do all these things, finally, the result for small mixing parameter looks as follows. V1 is related to Vn, and M1 related to Vn, being proportional to a number of small coefficients. And the idea is that, one can relate some high scale with some low scale, being a result of product of a number of small factors, which we don't know, of course. There are a few nice things about that particular model, particular chain. First of all, one can write the generic mass matrix in this case. And in fact, it is quite easy to understand that those metrics can be exactly diagonalized. Indeed, you see, you may diagonalize this corner with a rotation, and then it appears here. Second corner, you may diagonalize it with the second rotation, and so on and so forth. And expressions in this
Все, значит, надо попасть в это, ну, только они маленькие, пальцем не попадешь.
Okay. But at least the matrix is diagonalizable, which is quite interesting mathematically. Another thing with this model is that you may expect that huge hierarchy problem should appear, because if you take those scalar at level 1 and compute loop corrections from interaction with the scalar field at the level I, the the contribution to the mass shift would be proportional to the squared mass, large mass, times a log. But if one looks carefully what the coupling in front, you end up with the expression which is proportional to the m times number of that small coefficients, and it gives exactly the value of the mass m1. So in this sense, the little hierarchy problem doesn't show up, or at least it gets no worse than it is in the standard model. Let me come to a few comments. In this, of course, funny toy model, which I just described you, negative mu squared in question mark at our scale is induced as a result of those spontaneous breaking chain at some other higher scales. And in this sense, the hierarchy problem might be understand due to product of small factors being proportional to small mixing parameters. In fact, as some mathematicians told me that the construction is rather interesting mathematically. This chain is quite interesting. So you see at each level we have sort of conformal theory, and then it is violating on the very high level, and so that's I don't know. However, in order to make this toy model somehow more realistic, one to address many questions and resolve many issues. And all that is not done, and some of the things are in progress. Of course, we should understand quantum corrections better and renormalized group evolution in that sort of scenarios with proper matching at each of the level. Collider phenomenology, from the first glance, it looks like no difference between just simply two-level Higgs particle models or so. And if there are some unique observational signal, well, this is probably also not the case. One is the characteristic feature of the model that the far some level is from the first level, the lower interactions, the weaker interactions will be on that new fields on that level with the first level. Of course, a big question without cosmological implications, because definitely having several that levels, there are more degrees of freedom. It would change the evolution, and I don't know, do the symmetry breaking in the chain happen simultaneously or at different temperatures? Somehow one should also think about and analyze that. And in order maybe to answer the question, one should put some concrete examples, which concrete Lagrangians on one or two levels of the chain, and apply these examples to address the dark matter issue. What I would like to stress here is that standard scalar portals in context of dark matter was the study of many papers, and usually, the game is that one should have some model with some parameters and try to satisfy several restrictions. And this list, for instance, is implemented now in Gambit code, and one can use Gambit code in order to make this, namely theory constraints from unitary behavioral scattering amplitudes, you should get thermorelic abundance. And we have more parameters in that model than usually, so that probably not that difficult. Of course, one should, take into account constraints from Higgs invisible decays, from indirect dark matter detection, from direct dark matter detection, and dark matter capture and annihilation in the sun. And as I said, these things are implemented in Gambit code, but these things always could be improved or added things. So thank you, Dima, and I'm pretty sure that you have more concerns, more critics about all this construction. So thank you very much.
Thank you very much. So questions?
Things are so simple that
Simple but complicated. All right, so any questions from the audience or from Zoom?
May I from Zoom?
Yes, please.
You may naively make perturbation calculations and improve by renormalization the negative sign of mass square, or not? Not making shift as a condensate, but naively by negative mass square propagator calculate perturbation theory and just by renormalization procedure improve. We improve even infinite corrections. Why not? We can improve just sign or not.
Yeah, in fact, the negative sign it might cause by radiatively. Of course, we know that in the standard model, radiative shift is not enough to make the proper Higgs field, but you are right that can be done from the evolution, starting from another field. As I said, this question is not studied, and it should be studied. Thank you.
Thank you. Any more? Let me ask you, if you have this sequence of models which you presented, so in principle, what you expect might be the indication of their existence?
Yeah, as I said, it's a good question, Dmitry, thank you. First of all, the indication would be to see the next level, or the closest level.
Yeah, the closest
level. In this respect, there is no much difference between just two-level models, which is Higgs particle model or scalar particle model, the usual Higgs. However, the prediction is that if you have something here, but on the next level, you have states which are much weaker interacting with the standard model.
And then it's very hard.
It would be even harder to discuss, but that is a prediction. So what?
No, but in principle, if you have at least two levels, then you should have heavier Higgs, Higgs-like particles,
absolutely,
which we expect to see at the accelerator, right?
Yeah, absolutely. But these things are known very well, and that's what people were
like two Higgs doublet model.
Yeah.
So it's the beginning of the chain.
Yeah, that's right.
Huh?
The interaction here is not just two Higgs doublet.
Yes, it's different. But at least this particle should exist, right?
Yeah, there is one more scalar, or several more scalars, but that's not quite.
Not exactly like the Higgs doublet model. I agree, because the interaction is different. But some indication should exist, right? Yes.
Yeah, what can keep these mu's, except for the last one, for the largest n, what can keep these mu's equal to 0? That's relatively unstable, right?
Right.
Is it?
No, well, it's a good question. So strictly speaking, I don't know the answer, but in fact, sort of approximate conformal symmetry. That what because if you don't have mu parameters and you have conformal series at each level, and violation comes from the very end, so it's sort of small violation of conformal symmetry. But right, but amount of that violation, at least at our level, is not enough to we know that Kuhlmann-Weber potential is level doesn't work properly for our
It might be problematic to have stability.
But yeah.
All right. So
Maybe one question.
yes, please.
Thank you. Does it turn out in this model that indeed we'll have the set of Higgs bosons with approximately equal masses?
Well, here in this construction, in the limit which we considered mostly right now with small mixing parameters, that is not the situation. The situation is somehow one mass of the Higgs is much larger than another, and so on. But as I said, the mass is exactly diagonalizable and mathematics. And that assumption is not necessarily one could make. And then this chain might be quite interesting mathematically, looking for some maybe non-perturbative effects. And then probably something will be, as you mentioned.
Okay, thank you.
Right. So if no more questions, then we have a coffee break.
Thank you.
Dear colleagues, let's continue our morning session. The first speaker is Professor Akhmedov. The title on the blackboard, please.
Is it on? Yeah. Huh? Okay, so I will talk about some research which I have done already for more than 10 years, and it is summarized in this short review. Yeah, there are too many things that in principle one can say in this scope, so I have to restrict myself to some certain things which are more important than the less important things. So let me start with the general idea that the goal of quantum field theory is to calculate correlation functions, which are building blocks of observables. For example, you can using correlation functions, one can calculate amplitudes, etc., etc. And usually we, in high energy physics, we calculate amplitudes and wire them cross sections, and in condensed matter theory, we usually calculate various sorts of currents, fluxes, etc. So in high energy particle physics, one uses only Poincare invariant states in high energy particle physics. For such states, correlation functions are analytic functions of geodesic distances between, so they do not depend on each coordinate, each point separately, they depend on geodesic distances. In condensed matter theory, one frequently restricts attention to stationary thermal states. In such a case, correlation function may depend on spatial coordinates separately, but on times, they depend on time differences. It is the point of stationarity. Stationary means that it doesn't depend on the moment of time, it depends on the time difference. Or in condensed matter, people deal with slight deviations from such a case, which are close to equilibrium, such that quickly relaxes to the equilibrium. I would like to stress that the action of the theory can be perfectly Poincare invariant. You can take, for example, scalar field theory, which is a Poincare invariant theory. But the state of in such theory, one can choose such that correlation function will have either such form, or even more complicated form. So there is a good reason that we consider such correlation functions, because present-day universe is actually very close to equilibrium. So even if we consider processes out of equilibrium, they rapidly relax to the equilibrium state. But what is more miraculous is that common wisdom is to consider also isometry invariant or very special states in de Sitter spacetime, while we assume that de Sitter stage, well, now it's also our universe looks like de Sitter, but with very huge radius, such that it is also very close to stationarity. But in early universe, we also restrict our attention frequently to special states, which are symmetric, etc., which I find odd, because it sounds to me like as if you do the following: you live in the delta of a river and see the flow of water, which is luminar, and you say the same sort of flow is there in the source of the river in the mountains, which is obviously shouldn't be the case. Obviously, in the early, when I'm saying about early universe, essentially I am discussing the state from which the universe has started, like at the beginning of even de Sitter phase, not at the exit of de Sitter phase, but at the beginning of de Sitter phase. In the early universe, if its metric was truly very close to de Sitter one with God scale curvature, the situation was highly non-stationary. There is no reason that the Radcliffe expansion has started from a highly symmetric state with isometry invariant correlation functions, or a thermal state. It means that the state we have started was generically, supposedly, was like this. Correlation functions were functions of each point separately. Furthermore, the metric was only approximately equivalent to the de Sitter one. You see why I'm stressing that. In the de Sitter space, you also can consider such correlation functions, which are functions of geodesic distance in the de Sitter space. The de Sitter space is highly symmetric space. It's as symmetric as Minkowski. So after rapid expansion, such correlation functions can become almost spatially homogeneous, means that they will start to depend on differences of spatial coordinates. But that doesn't necessarily mean that spatial homogenization will be accompanied by equilibration. You see, it doesn't necessarily mean that simultaneously it will happen that it will stationarize. It means that even becoming spatially homogeneous, it can still depend on the times separately. So it still can be non-stationary. When the curvature of the universe was, there is a good question what was observable in those days. You see, if you, obviously amplitudes are not good variables in these stages. Like for example, amplitudes and cross sections are not good observables even in plasma or at finite temperature. It goes without saying that in early universe, the conditions were even stranger and more special. And good observables are actually correlation functions of stress energy fluxes, but we cannot observe them directly. We can observe them only indirectly via the effect they have on the background geometry. Of course, I'm talking here about the situation when the gravity is treated classically, quasi-classically, while all the other fields quantum. And moreover, because the field was always on, gravitational field was always on, there is no reason to assume that the stress energy tensor was separable into anything like particles. So there was no notion of particle. Sounds like I am considering something absolutely crazy and untractable. But in fact, quantum field theory does have a tool to calculate correlation functions, even in such unusual conditions. But what is very strange in comparison with the situation we are usually dealing in high energy quantum field theory is that to get an unambiguous answer for correlation functions in such non-stationary situations, one has to specify an initial Cauchy surface, a basis of modes, which is also ambiguous, and an initial state, and then use the Schwinger-Keldysh rather than Feynman diagrammatic technique to calculate correlation functions. In the described circumstances, what is even more striking in comparison with the situation we are used to in high energy physics, in the described circumstances, loop corrections do not just lead to UV renormalization of various coupling constants. They also contain infrared secular memory effects, which are totally absent in equilibrium. These loop effects are sensitive to initial and boundary conditions. That's the reason you have to deal with these issues. And they can provide the corrections to correlation functions, which can be even greater than 3-level contributions. So 3-level contribution to correlation function is negligible with quantum corrections. That can happen in non-stationary situations. Why is this important? It happens that if, for example, correlation functions are not isometry invariant, if correlation functions are not analytic functions of geodesic distances, then expectation value of stress energy tensor is not proportional to the metric. It doesn't lead just to renormalization, UV renormalization of cosmological constant. It can also lead to screening of the cosmological constant, quantum screening of cosmological constant, screening with time. And the initial state of the universe which had God-scale curvature, doesn't have to be thermal state of standard matter, dust or radiation. It can be any quantum state. We don't really know which state. And what I'm saying is that we have to study all possibilities as much as we can and see which of the possibilities leads to the proper observational cosmology. States with Planckian distribution, what is interesting, states with Planckian distribution with temperature, thermal states in curved backgrounds for exact modes, they obey the fluctuation dissipation theorem. But for generic temperature, non-canonical temperature, the corresponding stress energy tensors are singular on the horizons. So these are not real thermal states in proper sense, which is a very unusual situation. Is just to tell you that if you say about thermal state in early universe and treat it as if it is for exact modes, it has problems like this. And this is the list of the papers where you can see the related discussion.
Which exact mode do you take into account?
Sorry? Which exact mode?
Exact mode, because
well, it depends on.
In any curved space, even in de Sitter space, there is infinite many ways to introduce a particle.
Mm-hmm. Infinitely many ways to introduce. Actually, there is infinitely many ways to introduce modes also in flat space, not only in curved space. You can use curvilinear coordinates, etc.
No.
And
in flat space, you have the Minkowski coordinates. Then the mode can be defined from the Hamiltonian to be positive defined.
If you insist on that, but you can, for example, consider a patch of Minkowski space, for example, Rindler patch, and consider exact modes there. Then you have the same problem.
Yes, you have the same problem.
You mean, I mean the same problem as I described.
Same
here.
problem.
So, so if you consider modes, exact modes, you can choose any exact modes, basis of exact modes in the curved space, and take thermal Planckian distribution for it. For generic non-canonical temperature, correlation function will be singular on the horizon, and corresponding stress energy tensor also will be singular on the horizon.
What does it mean, the non-canonical temperature?
Non-canonical is that, for example,
no
canonical.
Higgs ensemble?
Yeah, no. Canonical temperature is the following. In Rindler space, it's Unruh temperature. In Schwarzschild space, it's Hawking temperature. In de Sitter space, it's Gibbons-Hawking temperature. If the temperature is not of canonical type, the correlation function is not function of geodesic distance, and then you get in trouble. So let me start from the very basics. I'm sorry to lecturing you about some basics because this is important. Some features, I gave you just a flavor of idea. Now I'm going into technical details. I don't know how much I will be able to tell you. So consider if you want to calculate time evolution of correlation function, of a correlation function. I have wrote it for a single operator, but that can be extended to multiple operator. And consider averaging with respect to an arbitrary state. It can be also a density matrix rather than a pure state. It doesn't matter. What I'm saying is the same. So this is a definition of the time evolution of this correlation function. And we know, suppose we know the initial value of this expectation value. So then we can calculate this quantity. Here is a full, H is a full Hamiltonian. This expression is true both in Schrödinger and Heisenberg pictures. In the interaction picture, this is equivalent to this, where S is an evolution operator, which becomes a S matrix if you extend this to minus infinity and this to plus infinity. And what is important is the presence of the dependence on T0. T0 is initial time at which you know this expectation value. So you see here the dependence on T0 in general doesn't disappear. So you have a dependence on initial Cauchy surface. When does the dependence on T0 disappear? In the equilibrium situations, the dependence on the initial Cauchy surface does disappear. But we have to have very special situation. The speciality is in the following sense. The normal ordered Hamiltonian, free Hamiltonian, is time independent and bounded from below. That's the first condition. Second condition, the expectation value here is taken not with respect to a generic state, but to a state which is ground state of the normal ordered Hamiltonian. And we also should turn on and switch off the interaction term adiabatically. If it is like this, then the dependence on T0 does disappear, because then under such conditions, the evolution from the ground state to ground state is basically the phase. And the evolution to any excited state of the Hamiltonian is 0, because you cannot, by adiabatic turning on and switching off interaction, excite the state of the theory. And then the dependence on T0 does disappear. In fact, you can put into here, unity. Unity is the sum over all possible states of the free Hamiltonian. And then the only state from the sum which contributes to this is the ground state because of these conditions. And then you arrive at this expression. This is how you derive Feynman diagrammatic technique. You can see that in any textbook. And everything time ordered here, upstairs and downstairs. That's the only special situation when you can use Feynman diagrammatic technique. And that is one of the two situations where the dependence on time, on initial time disappears. Another situation when you have a thermal state. But there it works a bit differently. So let us go further. But if you take an average with respect to a generic state, you have to calculate this quantity directly, starting with initial time T0. And the dependence on T0 doesn't disappear in general. So consider e.g. Example given quantum field theory with self-interaction, scalar, real scalar, massive field theory. And in the background like this. The mode expansion of the field operator is as follows. And to have proper commutation relations for A and A dagger and phi and conjugate momentum, you have to have that this guy here solves Klein-Gordon equation for this theory. In the Schwenger-Keldysh technique, every field is essentially characterized by two propagators. One is retarded propagator. Also, there is a second related to this one, which is advanced propagator, but it doesn't matter. This propagator is state independent. You see, the commutator here standing is a C function, so it doesn't depend on the state with respect to which you average. And it characterizes essentially the, how you call it, the spectrum of the theory, what sort of fields you have. This propagator is state independent. And also there is a second propagator, which is called Keldysh propagator. It does depend on the state. Here, this curly brackets is anti-commutator. Anti-commutator does depend on the state. And for spatially homogeneous situation, if the state respects spatial homogeneity, I'm describing simplest situations. If the state respects the spatial homogeneity, you have here level population and anomalous average. Anomalous average. You see, I'm considering spatially homogeneous state. And this is, this N is essentially this guy, you see. And here is the density matrix. The only thing I assume about this density matrix that you can use Wick contractions, Wick's theorem for it. Because for generic state, you cannot use Wick's theorem and then calculation becomes wild. So, for example, you can consider in Minkowski space-time. In Minkowski space-time, there is a natural choice of modes, as you say, where omega is the dispersion relation. And if you consider a state for which anomalous average is 0, but level population is not 0, but not Planckian, and calculate two-loop correction to the Keldysh propagator in this limit, that you take 2 points of the correlation function to future infinity, but keep the distance between them fixed. In such a limit, loop correction to the propagator, to this propagator, has the same form as it is. Like, I mean, it doesn't essentially change. The only thing changes is this guy. This remains 0. This guy receives correction. And the correction looks like this, where I is equal to this. This is nothing but collision integral. Collision integral. It describes quantum collision integral, Boltzmann collision integral. It describes the following processes. Essentially, what you see here is that the level population due to quantum corrections changes. You see, these two contributions describe two competing processes, that two particles collide, create two other particles, and this is a gain process. During the scattering, we gain particles on the level P, and this is a loss process. Due to the scattering, we lose particles from the level P. What do we see here? Look, pay attention. We see here violation of time, already in this simplest situation, we already see violation of time translational symmetry. You see, three-level correlation function, this guy, or this guy, when this is 0, they depend on time difference between T1 and T2. Because if you plug here this exponent, you have time difference. But in the loop corrections, time translation symmetry is violated. Starting from T0, level population starts to evolve, change in time. You see, this is average time, and this is initial Cauchy surface. Essentially, we have infrared catastrophe. You see, you cannot take T0 to minus infinity. You cannot shift it to minus infinity. Even after UV regularization, in this case, loop corrections will be infinite if T0 is equal to minus infinity. So this is very unusual in comparison with the situation we used to in particle physics. This is the second thing which I wanted to say. What is interesting for Planckian level population, if NP is equal to this Planckian, the collision integral vanishes. You see this term, this contribution, you see, I'm keeping only leading contribution to the correlation function in this limit. only leading contribution. This leading contribution vanishes for the Planckian distribution because this guy is 0 for the Planckian distribution because of this guy, because of this delta function. Due to energy conservation, level population doesn't change. This is it has dynamical equilibrium. And what is so this is only for Planckian distribution happens. You see, this is another. I told you that there is another situation when another stationary situation. Stationary situation when we deal with Planckian distribution. How you call it? When we deal with thermal distribution. Otherwise, if the level population is not Planckian, any other, this guy is not 0, and we have this secular growth. This is a secular memory effect. Secular, it remembers initial conditions and depends on time and etc., etc. This is the simplest situation when we encounter secular memory effect. What is interesting, even if lambda is small, after a long enough time evolution, the secular loop corrections becomes of the same order as the tree-level contribution, or becomes even greater. You see, you started with this guy, but this guy can become greater than this one. This is what I'm saying. I'm describing to you loop corrections, and they can be much bigger than tree-level contribution. They can exceed, even in this simplest situation. Of course, in this simplest situation, we know what happens. We know what happens. Unlike UV renormalization, in this infrared case, there is a clear grading between contribution of diagrams. You see, we are discussing infrared contributions to the diagrams. And in this case, we can see which diagram contributes more, which diagram contributes less. You can find, and if you want to resum these contributions, you obtain classical kinetic equation. Classical kinetic, Boltzmann kinetic equation, with the only difference that this collision integral is a quantum collision integral. You see, in Boltzmann collision integrals, this is negligible with 1, and this negligible with 1. So in Boltzmann collision integral, you have this difference only. Otherwise, you see, you calculate quantum loop corrections, and you find, take infrared limit, your internal legs sit on mass shell, and you find, I won't have time to say everything I wanted, but at least I said you essentials on the simplest situation. What if we, even in such a simplest situation, in this situation, choose modes as follows, Bogoliubov transform modes? Well, of course, we have to demand conditions that this is equal to 1 to have proper commutation relations for the ladder operators and for the field and conjugate momentum. And also we should demand that this beta goes to 0 as omega goes to infinity to have proper Hadamard behavior of the correlation functions. You see, proper Hadamard behavior of correlation functions is necessary to have proper UV renormalization. UV renormalization depends on kinematics, on the number of degrees of freedom, essentially. Beta function depends on the number of degrees of freedom. If you do not insist on this, number of beta function will depend on this coefficient, which is odd. You can essentially measure by measuring running of the coupling constant, you can see that the modes are chosen wrongly. This is odd. And to describe dynamics close to the equilibrium, now one can derive kinetic equations in this case, but in this case, kinetic equations for the level population for the anomalous average. And close to equilibrium, you can see that if beta is small, thermalization also happens. You see, how do you derive kinetic equation? Essentially, when this guy changes slowly, you subtract this from this and divide by this, you get kinetic equation. Here already you see kinetic equation. You plug there not the initial value of n, but the dynamical value of n. And you see this equation which describes to you evolution to the equilibrium. This equation is solved by thermal state. And the same you can see here, we showed in this paper that anomalous average will go to 0 and n will thermalize the level population. But that is not true in curved space-time. You see, let me summarize because I don't have time to say other 5 transparencies. We know that in flat space, essentially, if we take a reasonable initial state, it will thermalize. I even told you that even if you consider anomalous averages within the reasonable assumptions and conditions, it will thermalize. Of course, we don't know what will happen to a generic state, even in flat space. But it goes without saying that nobody so far can understand what will happen with a generic state in de Sitter spacetime. Because it can happen that instead of thermalizing, it can go wild, that the level population will blow up within finite proper time. You see this n here in the Sitter space, this n is comoving n. It's not physical, it's comoving n. And it can explode within finite. We see in some cases that even for massive fields in global de Sitter spacetime, and in the corresponding system of kinetic equations, n blows up within finite proper time. So instead of thermalizing within de Sitter spacetime, n blows up. You cannot neglect back reaction on the geometry, and thermalization probably will happen only after taking into account back reaction effect on the geometry. And it goes without saying that even more miraculous things can happen for more generic situations. You see, people usually consider very special states. For example, either de Sitter invariant states or their analogs for the massless fields. They do not consider excitations of these fields. In Minkowski space, we do not restrict ourselves always to Poincare invariant states. We say, look at their excitations, slight excitations, and we see that they relax. Probably that is true if you see some small deviations from de Sitter invariant states also. But consider a generic state, and it can go wild. It won't thermalize. It won't relax to the de Sitter isometry invariant correlation functions. And we see such examples in our study. So I'm done.
Okay, thanks to speaker. Any questions, please?
I'm sorry, I want to understand your statement. You said that if you have large enough perturbations, then it will not thermalize, or you don't know whether it will or not.
I see examples that it doesn't thermalize. And so I know such situations that it doesn't thermalize. And I assume that it's a generic situation in de Sitter space, meaning that.
So you have at least one example.
At least one example that it doesn't thermalize. Okay. Within kinetic approximation. And this is an approximation, also close to equilibrium in a sense.
So if you take into account quantum fluctuations in more appropriate, so to say, way, then it can
have even harder consequences. You see, people usually say that nothing horrible happens in de Sitter space by considering only very special. It's the same as if you study equilibrium of a pencil standing like this, switching off all the blows of the winds. And they say, everything, okay, it stands.
When you say the words like quantum corrections, that means that first you quantize everything, right?
Not the gravity. Gravity is quasi-classical. I quantize scale, in this case, scalar.
Matter. You quantize matter in the background of this.
Yeah, I'm working in the circumstances that gravity is still quasi-classical, but all the rest is quantum.
So all these corrections are due to usual particles.
Yeah, like.
And what is the difference when you quantize it in this background? You mentioned infrared and ultraviolet. In which case you have the difference? In infrared case, or
I am discussing infrared corrections. So, well, of course, it's infrared, but still of God scale. You see, I'm discussing de Sitter space of God scale, and the quantum gravity is still classical, but all other fields should be quantum.
Yes.
From the Hamiltonian, an interaction called Hamiltonian restricted from below.
From what?
Spectrum is restricted from below. You have
no, it's not restricted. In de Sitter space, you mean in flat space?
H0 is restricted.
In flat space, it's restricted.
Background.
Mm-hmm.
In that case, the time observable is not well defined. What if we have not that restriction?
Well, in the sitter space, we don't have this restriction. Still can work in the sitter space.
Okay, some question from Zoom. What else?
Valera wants to ask.
Some question from Zoom. No question from Zoom. I don't see. How to switch off?
Sorry, there was 2 questions from Zoom. Are you ready to ask them?
Yeah.
Yes.
Yes, please.
Emil, this is Augusto. Hi. You are working on quantum field theory on fixed sitter background, but you know there is a lot of diffuse feeling in the community that the sitter space globally doesn't make sense. How would you try to connect? I mean, these problems that you're being confronted with resonate with the idea that the sitter space could be sick. Can you make a comment?
I don't understand in which sense global de Sitter space doesn't make sense. It's perfectly well-defined situation where you can set up initial problem for the calculation of the expectation values that I told you.
Well, it's not me, but there are many people that around.
Well, they encounter difficulties with calculation of amplitudes there, but that's meaningless to calculate.
No, not only that. They have some arguments of non-perturbative nature, like Valley, for instance, that they try to argue that there is something sick about the sitter space. Or if you want to, in theories like string theory, it becomes very difficult, I mean, to achieve the sitter space. Although we know that it should be achieved in a quasi-de Sitter setting within inflation. I just wonder whether this kind of results of having corrections which are bigger than the original term could be interpreted in terms of an instability or a sickness of the sitter space itself. You're not thinking in those terms, or perhaps?
Well, I am essentially discussing a related problem. By instability of the sitter space, at least what I mean, and as far as I know Polyakov means, is that by instability we mean dynamical screening of the cosmological constant. And in global de Sitter space, if you calculate correlation function, it's perfectly well defined, but it has the same sort of infrared singularity, like this one, exactly like the one on the central formula on this slide. You have this T0, and you cannot shift this initial Cauchy surface to minus infinity. So probably people say that this is a problem for global de Sitter space. But I don't see it a problem. You have the same problem for a generic state in flat space. You know what, then after a summation, what happens? But in de Sitter space, we did the same resummation in global de Sitter space. And we see that under some conditions, level population blows up.
Maybe the next question from Zoom.
Okay. Yes, okay. Thank you, Emil, for that was very interesting talk. I would like to remind the old and recent result of my groups, in particular speaking about quantum field theory of say minimally coupled and interacting scalar field. So m squared phi squared plus lambda phi 4 in the de Sitter space-time. In this case, the statement that for positive m squared and even in the Higgs case, but let's not speak about it. The results for such more measurable quantities, not n about which you spoke, but for example for average phi squared, they are finite and actually in all loops, and this was obtained using a rather old but non-perturbative method, what is called the stochastic inflation. And what we have done recently, it was our just recent paper which appears last month with Alexander Kamychik and Teresa Vardanyan. We just check this, okay, say non-perturbative approach, but by the standard field theoretic methods. It was previously checked in one loop order, but we now make a next step and check it in the second, in the two loop order, and we indeed see that the stochastic approach gives first finite, the value for y squared, and second the same value as was predicted by this non-perturbative approach. And indeed, the subtle point, which is related to the previous equation by Professor Sanyotti, and actually Emil mentioned it in some sense too, that really we consider not the global decitic space time. We consider the so-called Poincare gauge. Yes, and this Poincare gauge just refers to what we really have in all real viable models of inclusion, because it is intrinsically assumes that the decitic stage was not eternal in the past. And actually, this may occur for different reason, and the most natural, which appears even at the level of classical gravity, even in the simplest case, classical gravity with a cosmological constant. Previously, there was some more singular space-time, actually the singularity, and then it's known that in this case, the sitter is generalized. The sitter is the generic late time asymptotic, but then it naturally appears just in this Poincare gauge. So I would say, I admit that there may be problems, just as well-known problems, say, even at the level of classical dynamics, if you consider properties in the constant electric field, and if you assume that it was a constant up to t minus infinity, but no, all problems disappear if you turn on the electric field at some moment of time. I would say that for such problems, which are more related to viable inflationary models, when we have the set of time emerging at some finite moment, then indeed we see that at late time we have this asymptotic behavior.
Mm-hmm. Yeah, essentially, let me summarize what you have said. You see, this is, two words, essentially, 1 minute. This is Penrose diagram of de Sitter space, of two-dimensional de Sitter space. Essentially, this is stereographic projection of de Sitter space. This is glued to this. It's a cylinder. This is the dotted region is expanding Poincare patch. This the complementary side is a contracting Poincare patch. You see, there is a difference between Cauchy surfaces. In expanding Poincare patch, Cauchy surface is like this. In global de Sitter space, Cauchy surface is like this, and in static patch, which is a velvet region, Cauchy surfaces are like this. And depending on which Cauchy surface you choose, because of the secular memory effects, quantum corrections do depend. They change. You see, essentially, you change. You choose different reference system, different coordinate system. It seems that how can it be that correlation function does depend on the reference system, on the how you call it, on coordinates. And that is true if the correlation functions are functions of geodesic distances. They do not depend on coordinate systems. But if you consider situations more complicated, and in the Sitter space, what is fantastic, even for the three-level symmetric state, because of this infrared catastrophe, which I told you about, everything depends on which initial conditions you have chosen. So in global de Sitter, what Alexei said, that in Poincare regions, they do not encounter any troubles. They calculate troop corrections for the special state on this surface, and everything perfectly well defined. But what I'm saying that if you try to calculate the same sort of correction in global de Sitter, you encounter troubles. You get, everything perfectly well defined, unique, unambiguous, but have problems.
Thanks. More questions, please. No, I have
so once more, only I want to say, so it's not a problem of choosing a gauge of a reference system. It's the problem of choosing physical and initial conditions at some moment of time.
I am choosing physical initial. I am choosing, for example, Euclidean state here, and I get in trouble. Euclidean state perfectly de Sitter isometry invariant at 3 level, but loop corrections violate de Sitter isometry. That's what I'm choosing, what I'm saying. For any initial state, you get, like, for example, I told you here, even in flat space, you choose any distribution, initial distribution, which is not Planckian, and you run into loop corrections which secularly grow. The same thing you encounter in the Sitter space.
Emil, once more, my request is to present quantities like average phi square or average square of the energy momentum, because the quantity which you use, the number of particles,
you get into trouble with energy momentum tensor also from this.
You don't have any troubles.
We do,
well,
calculate with this level distribution stress energy tensor. It's a simple calculation, one line. You get in trouble.
Sorry, Alexei, he told his point of view. Okay, so let me say, you consider case with unstable vacuum. When you consider theory
with any space, vacuum, with any.
Okay, so you consider theory
with any initial state.
When asymmetry separator acting on vacuum is not proportional to vacuum. It's called the unstable vacuum. It is
well, there is no such a thing as a vacuum in time.
Let me say, sorry. It is characterized for non-euclidean statistical mechanics, and you really derive the Boltzmann equation. But usually people try to find the solution to Boltzmann equation not in the form of expansion in time, but it is known that any term in this expansion is secular. If you differentiate your relation with time,
you get Boltzmann equation.
Boltzmann equation.
Yeah.
And can try solve it like an integral differential equation.
Yeah, that's what I said.
And you get a different result.
Yeah, that's what I said. And in the Sitter space, you do the same and you get in trouble. That's what I'm saying.
Okay. Okay. So, consensus speaker again. So the next speaker is Professor Shaposhnikov. The title of his talk, Quantum Field Theory Without Infinities and Hierarchy Problem. He will speak through the Zoom.
Okay, I'm trying to speak through the Zoom and I'm not allowed to share the screen. Okay, thank you. Okay, so do you hear me? So first, I wrote for the Magnificent Seventh. Congratulations with the Jubilee, dear friends and colleagues, many happy returns. And thank you very much for organizing this exciting event. Happy anniversary. Since I'm giving a remote talk, I will have to drink also remotely, which I'm going to try this evening to congratulate you over this jubilee. Okay, so did you hear me?
Yes, yes.
Okay, and you see my previous slides, right?
Yes, everything is okay.
Everything is okay, fine, thank you very much. Okay, so I will talk about QFT without infinities and the hierarchy problem. I will start with some short overview of naturalness. Then I will talk about different finite approaches to QFT. I will present you some update of column semantic method as finite description of QET, and will demonstrate you that there are no divergences, there are no fine tunings, and then I come to conclusions. And the work which I am presenting you here is based on the paper which we wrote with Santer Moy, and which should appear on arXiv tomorrow. Okay, so introduction, Higgs mass fine-tuning. The puzzle, take the standard model and consider radiative correction to the Higgs mass. Okay, so these are different diagrams, one loop, and what you're gonna see that there are quadratically divergent diagrams. If you cut off this diagram with some UV scale lambda, where the lambda is the place where the standard model is substituted by fundamental theory of nature, then you find that you're in trouble. There are very large radiative corrections proportional to this large cutoff, and then you conclude that you have to fine-tune the tree value of the Higgs mass with the radiative corrections. And then the degree of fine-tuning, which is this difference, tree value minus radiative corrections divided by UV cutoff, is required to be much smaller than 1. Okay, so you get a similar problem in the vacuum energy. You can consider different loops. Now this loops diverge as a fourth power of the scale. You again conclude that the loop contributions to the vacuum energy diverge like lambda to the fourth. You organize, you construct your fine-tuning parameter, again, the difference between tree value and the vacuum value, and you find that this guy should be much less than 1. Okay, so you get essentially the same picture if you consider a Wilsonian approach to quantum field theory, where you say that I integrate out the degree of freedom at large scale. So in this case, you take the standard model and then you write down all possible operators of, I mean, the whole action should have dimensionality 4. So you write different operators. You find that there are 2 operators. One, which is essentially the Higgs mass, so H is the Higgs field. Another operator is the vacuum energy, which is proportional to lambda to the 4. This is lambda square. And again, you get the similar type of the puzzle. You ask yourself why this high energy contributions to low energy action should be compensated with parameters of your energy theory. So in fact, there are 2 problems here. So the first problem, I would say this is a physical problem, is why the physical values of the Higgs mass and of the cosmological constant are much smaller than the scale of new physics. Okay, here we know that there is a new physics, at least related to gravity, and why the Higgs mass is much smaller than the Planck scale, why the cosmological constant is much smaller than m Planck to the 4th, or you can take grand unified scales. So here we're comparing physical quantities, and it's certainly a problem. There is yet another problem which leads to the notion of so-called naturalness. So we can ask ourselves why the 3 values of these parameters are so much fine-tuned to the radiative corrections. And the naturalness paradigm says that this fine-tuning should be avoided at any price. And the consequence of that is that the cutoff lambda should be of the order of Fermi scale, so that new physics starts roughly above the Fermi scale. And then this new physics is organized in such a way that low energy domain of the theory is screened from the high energy domain of the theory, so that you make a variation of high energy domains, and this doesn't result in large variations in your low energy domain. And this led to formulation of many theories, such as low energy supersymmetry, composite Higgs boson, or large extra dimensions. There are more recent developments in which it is discussed that maybe it is cosmological evolution, which leads to the Higgs mass much smaller than lambda, or maybe there is some environmental selection, multi-universe or whatever, which means which leads to the Higgs mass much smaller than the cutoff of the theory, than the scale of new physics. Again, generically, these proposals lead to some kind of new physics right above the Fermi scale. Okay, so this problem attracts a lot of attention. So Oleg Ruchaysky, who has some bibliographic tool, made the following exercise for me. So you can count the number of articles which mentioned hierarchy problem or fine-tuning or naturalness. And here is this plot as a function of time. Okay, so you see that kind of visible deviation from zero started from Gildener 76 paper, where he said, he pointed out that there is this problem in grand unified theories. Okay, then the plot goes up with the, I mean, I don't have a real interpretation of all these different wiggles on this plot. This is just my hypothesis. Perhaps this growth is because of supersymmetry. This growth is because of large extra dimensions. This point, I think, corresponds to Higgs boson discovery. This extrema corresponds to 750 resonance. Okay, now this goes down. The naive extrapolation says that the plot hits the ground in 2030 or something like that, though this is a naive extrapolation. Okay, so what is the origin of the fine-tuning? Clearly, that the core of the problem are quadratic or quartic, if we talk about the cosmological constant, divergences. And these divergences appear inevitably in Feynman diagrams with loops in theories with fundamental scalar fields. Okay, so there is an ingenious way to take away these divergences, which is a renormalization problem. So what you do, you regularize UV divergences by some way. You can use cutoff, Pauli-Wheeler, whatever regularization, and so that Feynman diagrams start to be finite. Then you introduce counter terms, and the role of this counter terms is subtract these divergences. And the hierarchy problem or fine-tuning problem appears exactly in this way. Okay, you add something very large and you compensate something very large, and at the end you get something reasonably small. Okay, and then once you apply this procedure, you get finite expressions for physical observables. And this can be summarized on this plot. Okay, so you have, say, a renormalizable theory, like electrodynamics, which contains several finite parameters. In electrodynamics, that would be electron mass and the fine structure constant. Then you apply your procedure with infinities, regularization, counter terms, and fine-tuned constellations. And then as an output, you get infinite number of physical observables. So you get infinite number of predictions, different cross-sections, reactions, etc., etc. But in principle, the same type of procedure can be applied to non-renormalizable theories. Well, though, in this case, the number of types of counter terms which appear to remove divergences happen to be infinite. But still, you have some infinite number of finite parameters which characterize your theory. You plug it into your renormalization scheme, and at the end of the day, you can have infinite number of physical numbers. Okay, so looking at that, it's clear that, okay, so this is some box, right? At the end of the day, you're going from here to here, or you're going from here to here. And this suggests that there must exist a finite formulation of quantum field theory, in which you start, say, from renormalizable theory. You have an input, several finite parameters, then you do something, no infinities, and then you get an infinite number of physical observables. Okay, and the same is true for non-renormalizable theories. Okay, and now the question arises, okay, if we have a finite formulation of quantum field theory, there are no infinities, okay, no quartic, quadratic, logarithmic, none, okay? So perhaps in this case, there are no fine tunings, because in this case, all your expressions are finite, and the computation of low energy observables shouldn't require the knowledge of UV domain of the theory. Why so? Just because all the expressions are finite, all integrals are convergent. And so what happens at very high energies doesn't matter. And if such formalism really exists without large consolation, that would challenge the natural paradigm. Why so? Because if just one particular formalism of computation and quantum field theory without necessity of fine-tunings is found, it will provide a strong argument that the problem of quantum stability of electroweak scale against radiative correction is formalism dependent. And if it's formalism dependent, it's not physical, because I choose another formalism, and in another formalism, I don't have this type of problem whatsoever. Okay, finite formulations of QFT. Okay, the statement that there is a finite way is close to trivial, right? And of course, people did explore that in the past, and perhaps most famous method how to formulate quantum field theory without any UV divergences, it goes back to Bogolyubov, Porosuk, and Zimmermann method. So what you do there is that you have a certain procedure which is called R operation, and this R operation is applied to any Feynman graph before performing integrations over internal momentum. And so you change in this way the integral, okay, and then you got an expression which you integrate, okay, and then you get no infinities encountered, okay, and we can say that, yes, this is a new formulation of quantum field theory which doesn't have any divergences whatsoever, okay, and the R operation, as Dima underlined quite recently, can be used in both renormalizable and non-renormalizable theories. There is yet another approach, which, but it somehow happens that BPHZ procedure is kind of rarely presented as alternative to quantum field theory with infinities. Okay, so another thing which people discussed in the past is actually associated with the names Kalan and Simanchik, who invented, well, 50 years ago, equations which are used nowadays very effectively as a tool for renormalization group investigations of the high energy behavior of renormalized amplitudes. However, the inspired by Kalan-Simanchik method equations can also be used for construction of completely divergence-free and thus completely finite perturbation theory. Okay, so and this is discussed in Kalan lectures and more or less simultaneously by Blair Young. So these are pretty old papers, and I mean, this formalism is now rarely used for practical computation, but it's very helpful for the discussion of conceptual things such as hierarchical. Okay. More recently, well, it's 2004, well, 17 years ago, Tuft came out with yet another proposal how to construct the quantum field theory without infinities. So here, the idea is that you can consider diagrams at different momenta, and then when you subtract the diagrams with different momenta, you get entirely finite expressions, okay, and then you can write a set of equations which unify the finite, completely finite expressions. They look like renormalization group equations, but they are somewhat different. And then the parameters of the theories are just some initial boundary conditions for the Green's function there, and you solve that, and then you get everything without any mentioning of any infinities whatsoever. And potentially this equation may result in completely non-perturbative and divergence-free definition of quantum field theory. Okay, it's interesting also to look back in the history, and if you look at LSZ paper, the famous one, which is famous for its reduction formula. Okay, in fact, half of this paper discuss finite formulation of quantum field theory. Another interesting work is by Nishijima. Okay, so how this works. So what I'm going to do now, I select one of the methods. Okay, we selected Cullen-Szymanczyk method. And I will go through the steps which are needed to do computations in such a way that no divergences appear whatsoever. Okay, so the simplest lambda phi to the 4 theory, there is Lagrangian. Okay, the parameters m and lambda, these are finite numbers, no bare quantities, no divergence whatsoever. These are finite quantities. Okay, then another gradient there is the set of equations, okay? And these are the equations for strongly connected Green's functions and yet other theta-type Green's functions. I will tell you what theta.
Sorry, let me ask you.
Yes.
Okay. If you postulate this equation, does it mean that beta and gamma are unknown?
No. Beta and gamma are derived from, actually, these parameters which appear here happen to be related to different anomalous dimensions, and they are derived from these equations.
Okay, so that does mean the standard equations, no need to postulate, they can be derived.
Yeah, no, but here they can be derived, of course. I mean, of course, these equations are derived, and they are shown to be equivalent to BPHZ formulation, okay? So this equation can be derived, but now I say, I'm searching for finite formulation of quantum field theory, okay? So there is an infinite formulation of quantum field theory, which is based on different Feynman graphs and multiplicative renormalization. So that's one scheme. And here I say, okay, I postulate these equations, okay, period. And then one can show that the solution of this equation satisfies all necessary requirements which you impose for Green's function. So there is analyticity, causality, everything is satisfied. Okay. Okay, so these are these equations. Then,
sorry, Misha.
Yes.
How do you know what are these beta and gamma? If you postulate these equations, then you have to postulate these beta.
No. These guys are found. I come to that point. Okay, so look at this equation and wait for the next slide. Okay, so what also is postulated here? Okay, so first you postulate boundary conditions, and so most important functions which we are dealing with here are those with 4 legs and with 2 legs. And it is postulated, okay, so that's the part of formulation of quantum field theory, which is finite, is that this gamma 2, well, mass operator at k equal to square equal to this parameter, then the guy with 4 legs at k square equal to 0 is equal to the coupling constant, and this is a derivative. Okay, so if you use multiplicative renormalization, then the stuff would be close to on-shell scheme if you want. Okay, and now, so these things are postulated, Lagrangian, 2 equations. The parameters beta and gamma theta are not specified yet. Okay, these are boundary conditions, and now the things which are computed. So the first thing is which is computed is first order 3 approximation for 2 and 4-point functions, which are computed from this Lagrangian. Okay, and this is 3 approximation. Then what you do, you compute gamma theta 4 and gamma theta 2. Okay, and this is completely finite computation, which is the following. So theta operation is what it's doing is cutting the propagator in 2 pieces. Okay, so you can think about that as you take the free propagator and differentiate it with respect to m squared. Okay, so once you do so, you get here a finite expression. And for gamma theta to 2, you also get a finite expression. And that's it, okay? So now you use this equation here in a perturbative manner, step by step, doing first order lambda, second order lambda, et cetera, you reuse the results which you found at your previous step, and you find out all these unknown quantities which are related to anomalous dimensions, and you never ever get anything infinite on the way, and you can prove, and Cullen did that this procedure is equivalent to BPHZ, okay? So no infinities. Well, we can also say, okay, there are no infinities, but maybe if we have the theory with very well separated 2 mass scales, then we will encounter a problem. And of course, if we do conventional regularization, renormalization, etc., we do get so. I mean, for instance, so let's take the theory which contains 2 scalar fields. So little phi corresponds to light field, capital Phi corresponds to heavy field. So you have some potential mixing between the 2. And now, for instance, if you say, okay, let me use MS bar scheme, which is dimensional regularization, okay? If I take lambda phi to the 4th theory alone and use dimensional regularization, I won't find the fine-tuning problem.
Excuse me, 5 minutes to the end.
Yeah, I will be done for sure. Okay, and if you do this computation, then you find that the Green's function for light fields, it contains a large contribution coming from the heavy field because of this mixing. Okay, and you have to fine-tune. Now, you do your quantum field theory approach. You take the same Lagrangian as previously, okay? All parameters like m, lambda, etc., you take finite. Then you write down equations for these vertices and new theta-type vertices. So the amount of them will be larger because there will be a theta operation for little m and capital M. I don't write this equation here. They would take a lot of place. And then you have boundary conditions, which are again valid in all orders of lambda. Then, as exactly previously, you take first order 3 approximation for 2-point functions, no divergences. Then you compute one loop expressions for different MM functions. Now, there are also guys with one theta, which I don't write here. You plug it into your equations, so that iteratively, and then you find that in all orders, no fine tunings are needed. The parameters M and M physical are small. M physical is defined from the pole of the propagator, and M physical are large. Okay, you can do the same with cosmological constants. No problem. The only price to pay is that once you introduce cosmological constant, sorry, it has the same letter as cutoff, but now it's cosmological constant, you have to add one more equation and take into account that your theory contains one more parameter. So in addition to anomalous dimension for lambda, there will be yet another anomalous dimension for cosmological constant, and there is another object, gamma theta theta theta, which is written here, and which is completely finite. Okay, and then you use that, and then you get finite and tuning-free computation of all physical observables. And interesting physical observables here can be Casimir energy if you have space-time or space with non-trivial topology, or effective potential. So how did it happen that we arrived different conclusions in these two methods? Okay, so in fact, in all these approaches, the parameters which are standing there are just Lagrangian parameters which don't have physical meaning. So only at the tree level, they are directly related to physical observables. Now, if you include leap corrections, all these parameters are just the tools which convert a finite number of initial measurements, which define your theory, into prediction for new measurements of physical observables. And because of that, physical Lagrangian parameter do not carry any physical meaning, and so there is no physical meaning in consolation between them. Okay, and the unphysical of such fine-tuning is precisely proven by existence of Cullen-Simanchik method. It doesn't require any fine-tuning, but arrives at the same predictions for physical observables. So I'm coming to my conclusions. Finite formulation of QFT based on Cullen-Simanchik equation doesn't require any fine-tunings in theories with well-separated mass scales. And therefore, the so-called hierarchy problem, the sensitivity of low energy physics to high energy physics, depends on the formulation of quantum field theory. And if it depends on formalism, it doesn't have physical meaning, at least for renormalizable theories. And the conclusions, physics conclusions, which are drawn from two approaches are very, very much different. So if you say, okay, there is naturalness conjecture, then you are starting, okay, then you are living to a prediction of existence of new physics above the Fermi scale, which is used to screen the high energy physics. Now, if you use a finite approach to QFT, you cannot reach such a conclusion. Okay. Of course, I should say, so I split the problem in two, and the first one, namely, what is the origin of very, very much separated scales in nature, such as vacuum energy, Fermi, or that scale, this problem remains. Finite quantum field theory doesn't solve this problem. It just addresses the problem of consolation between tree and radiative corrections. And these are just remarks, so to say, the directions which it would be interesting to explore. We were discussing Cullen-Simanchik equations, a formulation of quantum field theory. It would be interesting to see what happened is the BPHZ, or its modification or Tuft formulation of quantum field theory. Also, non-renormalizable theories. It looks like that this type of logic may work, though the number of equations will proliferate and will be infinite. But still, the fact that we can apply theta operation as many times as we want look to promising. And at the technical side, So this theta operation is associated with the derivative with respect to the mass, and that doesn't work for gauge fields, for instance. Still, we think that this is a technical problem and doesn't influence on our discussion because this is associated with infrared rather than UV. And moreover, the TÜV method doesn't seem to have this problem. So thank you very much for your attention.
Questions, please. Okay.
Mikhail, thank you very much for this. Mikhail, thanks a lot for this remarkable talk. I have my question is the following. I thought that the essence of gauge hierarchy problem is that why electroweak scale is so small in comparison with Planck scales. So in other words, in the world without gravity, there is no gauge hierarchy problem. Because you mentioned quadratic divergences, but we know that in dimensional regularization, we don't have at all problems with quadratic divergences. So in this sense, of course, I agree with you. But
okay.
To my mind, people thought that there must be some physical cutoff, ultraviolet cutoff, and they thought that it's related with Planck scale.
Yeah, this is certainly correct. I mean, what you say, and I share a point of view. I mean, if you take indeed the standalone electroweak theory, then there is no problem whatsoever, at least if you neglect Landau poles, which appear in scalar self-coupling and in the U1 self-coupling. Then there is just one scale, there is no physics. Indeed, the problem appears when you get a new physical scale there. But here, I mean, when I started my talk, I separated two questions. So the first one, even if you have the theory with, once you have a theory with two separated mass scales, and of course we do have, so we have standard model and gravity, okay? Then the question that's why the Planck scale is so much compared with the Higgs scale, this is a puzzle, and this is a great question. But when people talk about naturalness, they talk about another thing. They're talking about consolation between tree parameters and loop corrections, and that's another problem. So I didn't address the first problem at all in my talk, but I did address only the second part.
More questions?
Misha, suppose you have the correct theory, the great grand theory is ultraviolet finite, so that everything is calculable without any, any problem. It's just finite theory. Do you think there is anything that relates your observations to the smallness of, we know that there's gravity, of course, with the smallness of the Higgs mass?
Okay, well, first of all,
in the theory which is finite.
Well, what I was arguing here is that lambda phi to the 4 theory is finite, okay? And what I was arguing that that the standard model is a finite theory.
No, I mean, ultimate theory, including the gravity, everything is finite.
Yes, but even theory with gravity can be formulated in such a way that it is finite. Okay, you should just generalize the Cullen-Semanchik equation or use the TÜV formulation. Okay, we didn't do that, but we suspect that can be done, and that the theory, even with gravity, can be formulated in such a way which is not based on Feynman diagrams, as I would like to stress, which is based on some a la Cullen-Semanchik equation. So you will get a completely finite thing. Okay, so
no, I mean finite theory. By finite theory, I mean, I say put the theory on a lattice and calculate everything on this lattice, and everything is finite.
Okay, so you say that let me use, for instance, multiplicative renormalization, and no counter terms will be needed in multiplicative renormalization. Okay, so yeah, I mean,
Mikhail, I can't agree with you about finiteness, because consider FIFO model for massless particle, for massless scalar. In this case, at quantum level, to make meaning of the model, you have to introduce additional some massive scale. So it's not conformal for massless.
True. But
the question finite, infinite, it's very subjective.
No. At this point, I do not agree, because you can easily describe the finite in a finite way, lambda phi to the 4 theory without UV infinities. The only thing which should be modified in this formalism, and I didn't go to that, is to change the boundary conditions for the Green's functions. Just take them not at k squared equal to 0, but some other value. And this other value will be associated with the scale you are talking about. But once this is done, you can write all equations, you can do all computations, and no UV infinities will show up.
I have, if I am allowed, a brief historical remark. In your historical survey, you probably should have mentioned the name of Ovsyannikov, because he wrote what is called now current semantic equations well before current and semantic in the end of the 50s. So you have functional equations from the renormalization group, and from that you derive differential equations, which are just current semantic equations. So it's even more just to call these equations Ovsyannikov Ovsyannikov current semantic equations. That's what I wanted to say.
Okay, so thank you very much. I didn't know that, and I will. It will be my duty to find out this paper.
Misha, that's written in the book of Bogolyubov and Shirkov.
I see.
So there is a chapter about renormalization group, and it's written there.
Okay.
Thank you very much. From Zoom.
I missed that.
Can I say a comment?
2 questions from Zoom.
May I ask question?
Yes.
Okay. May I ask question? I'm a little bit confusing, Misha, about what you are saying. You see, if we have a renormalizable theory, then it is okay, everything with current semantic. We can use so-called Zimmermann formalism, so working without any regularization, just to perform subtraction in the integrand, not to dealing with exact integral. Okay, what you are saying that there is something that we get from some kind of ceiling just to write some equation, some relation. Okay, we can write some equations, but we cannot prove that, we cannot prove without any perturbation theory that this equation came from some Lagrangian theory. In fact, we came to a similar problem when it was many years ago, by the way, we working in the close contact with Szymanczyk himself. It was about 77, 78, something like this. It was a problem to construct renormalizable 1/n perturbation theory. There, in some cases where we can, for example, so-called non-linear sigma model in 3- and 4-dimensional case. In that case, it was very useful to work in Zimmermann formalism and to prove with Kagan-Szymanczyk equation. But in that case, we had to incorporate perturbation theory. It was not so simple to how to say, to prove. But if we by some reason wanted to use a high dimension, work in high dimensional case where we know the theory is non-renormalizable, then of course we cannot prove anything. So I would like to say, just repeat once again, that we can do with what you propose supposed to do if we have behind us non-normalizable theory. This is fine. But if we do not have such theory behind what you're supposed to do, nothing you cannot do. So I'm sorry.
Okay, thank you
you
very much. Thank you very much, Ira. Just a few comments. So the first comment, the package I'm talking about, it does use Lagrangian, but not in a way it's done when you compute all Feynman grams. So the package contains the Lagrangian, the equations, and the boundary conditions, okay? And the statement which I made here is a statement which is entirely perturbative. Okay, so the question is whether this can be converted in an entirely non-perturbative approach. So perhaps is with the use of tooth method. So that's the first statement. The second.
Sorry. Let's go to next last question. Last question from Zoom.
Hello, Misha. This is George.
Hi, George. Okay.
So I have a short question. My question is about the work. About the cosmological constant you discussed. There is this, always people say about lambda to the 4 divergency of the vacuums. But there is an article recently was of Donahue, who calculated not only the T00 component, but also the pressure. And it is equal 1/3. So if you calculate the trace is equal to 0. Therefore, my understanding is that not just any energy contribute to the cosmological constant, but the trace of energy momentum tensor quantum should be non-zero. But if you calculate in vacuum loops, then you got the T mu nu is proportional to G mu nu, and the component is 1, 1/3, 1/3, 1/3, and therefore the trace is equal to 0. Somehow, that's what he said, that it is somehow there is no such problems.
If you have 1/3, 1/3, 1/3, 1/3, this means that you're breaking Lorentz invariance, that your vacuum state breaks Lorentz invariance. I mean, in the final formalism which I was talking about is completely Lorentz invariant. So I'm confused with that. Because, I mean, if you have 1/3, 1/3, 1/3, minus 1/3, don't you agree that this is breaking of Lorentz invariance? So it is.
Okay, sorry, let's stop discussion. I have no time for that. Send the speaker again.